Good morning, everyone. Welcome to the session on fault injection. We have three papers, three nice papers that will be presented by the authors. The first one is from Felix, who's going to talk about fault injection evaluation with statistical analysis, how to deal with nearly fabricated large CHES. Please.
Yeah. Thank you for joining.
Okay.
Yeah, thank you. Good morning. Thank you for joining. I'm Felix Uhle, and I will present you this joint work. Next. Thank you. So let's start with some short motivation introduction. When we have cryptographic algorithms, which are secure in a black box model, and we implement these algorithms, we introduce a new attack surface. Physical attacks, on the one side side chain analysis, on the other side fault injection analysis, and since we are here in a fault section, we will focus on the fault injection analysis side. Next. Yeah, sorry, but I have no pointer here. I have to say next for the next slide. Okay, and fault injection analysis requires the adversary to actively inject faults. He can do this by voltage glitching, laser fault injection, or, for example, electromagnetic fields. And then the adversary analyzes or observes the changed output behavior of the circuit, or maybe the unchanged output behavior of the circuit, and tries to learn something about the process secrets. We can defend against such adversaries on an algorithmic level using error detection, infected computation, which is a form of error detection where the output behavior of the circuit is randomized when error is detected, or via error correction. All of these countermeasures are again on an algorithmic level, so they work independently of the chosen physical attack vector. Next, please. And to say something about the strengths of our countermeasures, against which adversaries they work, we need some formal adversary models to do it in a formal way. Next, please. Yeah, thank you. And one of the first, probably the most prominent model, is the F-threshold fault model. In this model, the adversary knows the circuit. Next. And he can select up to F wires he wants to fault, and he can decide which fault type he wants to induce. Examples for fault types are stuck at 0, stuck at 1, or toggle faults. And the security parameter here, so which tells us how strong an adversary is the number of faults, F, that the adversary can inject. Next, please. And we have, so the security definition is the F fault security, and we have F fault security when all adversaries with at most F faults can cause for all inputs only ineffective faults. That means when the faulted circuit computes the same output than the non-faulted circuit. Next, please. Yeah, thank you. Now this F-threshold fault model has some limitations or some problems with the real world, and the observation is that in reality, when you shoot with, for example, electromagnetic fields on the circuit, and you have recent transistor sizes in your circuits, and you normally hit multiple gates with one fault attack. So it's not entirely true that one fault is easier to inject than multiple faults, which is somehow the assumption in the F-threshold fault model. And this model here, the random fault model, was proposed to overcome this limitation. And the idea here is now that the adversary is not bounded by the number of faults he can inject, but by the probability with that the faults that we have targeted occur. Okay. Short break. Yeah, I think we were here. So And since we have no probabilities with that the faults occur, we have in our security definition no binary decision anymore. So we have not secure, insecure, but we have some probabilistic statement about this security. And we say we have mu random fault security when the probability with that an effective fault occurs is equal or smaller than this mu. An effective fault means simply that the faulted circuit computes the output different from the non-faulted circuit. Yeah, and this model was then later generalized quite recently to the general random fault model, and we have here two major changes to the random fault model. The first change is that we now target or fault gates instead of wires, and the second probably more important change is that we have now one probability per fault set, per fault combination. I will use both terms interchangeable within this presentation. And this gives us a higher flexibility because now we can model dependent fault combination, dependent fault probability, sorry. And we have one probability per fault combination where we previously had one probability for each fault independent. However, this greater flexibility comes with the cost that we have to model a realistic fault adversary. Okay, the security definition stays the same, but instead of random fault security, now we have general random fault security, right? But no change here. And the objective of our work was primarily to investigate how can we compute the advantage, the probability with that an effective fault occurs efficiently. And to give you some intuition what the problem is with doing that, I will give you in the following a short example showing how we would do or could do this exhaustively, and then I will talk a bit about why this is problematic and how you can deal with that. Okay, so here we have a small example circuits, right? 3 gates, 2 ANDs, 1 XOR, 4 inputs, and we have an adversary, or we assume for this example an adversary that targets all 3 gates. So the adversary wants to fault G1, G2, and G3, and he can only apply set faults or stuck at 1 faults. And then we have here this table which shows us how much effective faults we have for each fault combination. A 0 below one of these tuples means the fault is not injected, and 1 means it is injected. So here no fault in this line is injected, therefore we have 16 ineffective faults since we have 4 inputs. And for each input, no fault is effective since we have no injected, right? Okay. When we fault G1, we have 12 effective faults, 4 ineffective faults. You can compute it by hand if you want. And for G2, the situation is the same since it's also an AND gate, also 2 inputs. For G3, it's a bit different, 10 effective, 6 ineffective, and so on. So we have to complete this table. And we will see that we have 70 effective faults. And using this number of faults, we can compute then the advantage of the adversary by knowing the probability with that fault set occurs. Here, for this example, for simplicity, we assume that each fault combination occurs equal likely, so we have 1 over 8. And we assume that each input to the circuit is equal likely, so uniformly distributed inputs, and then we can simply compute the advantage of the adversary by multiplying these both probabilities with the number of effective faults. The situation is a bit different when we have non-uniform distributions, since then we have to use a sum and we cannot simply multiply everything. However, not important for this example here to show you the problem, because the problem is that we have an exponential number of fault set input combinations, which makes it impossible to compute this exhaustively. For example, an AES has 2 times 128 inputs, multiple thousand gates if you want to investigate a real AES with all its rounds. So yeah, we can't simply do that. However, there are Verica Plus and IronMask Plus, which tries this exhaustively to some extent, so they add some threshold to limit the number of fault combinations we have to evaluate, which reduces the accuracy. I will explain that later in more detail. and both tools are only able to verify gadgets or smaller circuits. For example, for Verica Plus, I think can do one round of AES, but not all rounds, yeah, simply due to the complexity of the circuit. Yeah, what we do instead of doing or trying it exhaustively with some threshold or something like that, we do it statistically. And our idea or our approach is based on two observations. First of all, when you have a random experiment, which has two outcomes, then you have a Bernoulli trial. And this is what we have or what we can have for our situation. So we sample input fault combination. Yeah. And then we have two outcomes, fault, effective fault, non-effective fault. So we have a Bernoulli trial. And the second observation is that when we have n independent Bernoulli trials, then we have a Bernoulli process. And the number of an outcome of this random experiment of a Bernoulli process, so the number of effective or ineffective faults, follows a binomial distribution, which is parameterized about the number of simulations we conduct and the advantage of the adversary. And we exploit this knowledge that the number of effective faults follow the characteristics of a binomial distribution and our ability to simulate the circuit n times and observe how often an effective fault occurs. And this here visualizes our approach. It's a data flow diagram of the tool we have implemented, which is called Fiesta. And we have, so we sample n times fault set and input randomly with the user-supplied probability distribution. And then these randomly sampled input fault set combination is fed to a simulation engine, which simulate both the faulted and the fault-free circuit, and then we accumulate how often we have observed the effective fault. So how often the outputs of both simulations were different. And then we have a statistical step. And in this statistical step, we use the Klopper-Pearson interval to approximate the real advantage, the real mu, at a specific confidence level gamma, which is also user-supplied. Important property of this Klopper-Pearson interval for our use case is that's conservative. That means that the real advantage, the real mu, is always with probability gamma, so with the confidence, with the Z confidence level inside the boundaries. It can actually happen that the real confidence level is higher, but never lower. This is a property of the Klopper-Pearson interval. So yeah, that's quite nice for our use case. And here we have, as promised, some figures about the accuracy of Fiesta, our tool, versus Verica Plus. The green lines are Verica Plus, the blue and the red line. Sorry, the green lines are Fiesta, and the blue and red lines are Verica Plus. And what you can see here is that Verica Plus, for example, when you on the x-axis we have the probability with that a single fault is induced on a logarithmic scale, and on the y-axis we have the difference between the upper and the lower bound. So what we can see here, for example, for 2 to the power of minus 3, I think, for all depicted lines, it happens that the length of the confidence interval computed by Verica Plus is 1. So we learn simply nothing. And this is a dependency of Verica Plus on the adversary we want to evaluate. So it's not general purpose. There's some dependency. If the situation is the same for IronMass Plus, here they use the same technique. So yeah, no difference here. In our case, so for Fiesta, you can see we do not have such a case, right? We have for the light green lane 0.5 size of the confidence interval, which is quite huge. However, this only is because we did 64 simulations instead of, we can do 1 million for this easily for this example here. So yeah, we have no dependency in the end, which is the key message of this slide, on the adversary we want to evaluate, which is probably quite cool for evaluating every adversary in the generalized model, which had the goal to enable you to evaluate each adversary you want. Okay, we did also some case studies on on different protected AES implementations. And yeah, this here is our baseline. It's an unprotected AES. Again, on the x-axis are the probabilities with that an independent fault occurs. Again, on logarithmical scale, and on the y-axis on the left, we have the upper bound of the advantage, and on the right we have the size of the confidence interval, so upper bound minus lower bound. For each probability here, we did 1 million simulations, and we have assumed an adversary that targets all gates. And yeah, this is our baseline. And then here we have two different protection strategies. In figure A is the top one, and we have AES protected with a majority vote, so we have 3. This is a middle blue line, or 5. This is a light blue line instantiations of a AES, full AES, all rounds, which are all, so the full AES is computed, and then the output is fed to a majority vote. And what we can see here, that's the interesting point of this slide, is that already for 2 to the power of minus 17, the dark blue line, so the line of the unprotected AES is below the lines of the protected one, and that means simply that the advantage of the adversary, or the probability with that an effective fault occurs, is for the unprotected implementation lower than for the protected one. And the reason for this is that we have in a circuit protected with such a simple majority vote effect called fault propagation, which reduces the security level you will have in the end. Below, we have AES implementation protected with with the strategies of impeccable circuits too. The strategies prevent fault propagation, and therefore it is as expected. We have the weakest circuit. So the weakest circuit is the unprotected circuit. Then the circuit with 3 times redundancy, and then the best protected is the one with 5 times redundancy. Yeah, this is a few case studies. You have some more in the paper, but I think this was the most interesting one. Okay, so on all slides till now, we have assumed that our adversary wants or targets all gates. This is not necessarily realistic, because normally we will not fault in practical experiments all gates. So our idea was, our goal was that we try to derive some sets of gates that can be simultaneously faulted using some physical informations of the circuit we have. And for that purpose, we model local attacks, so all attacks where the fault location decides the set of gates that is affected simultaneously. This, for example, can model laser fault injection or electromagnetic fault injection if you assume that the sampling fault model is correct. And we use then such a rectangular shape to abstract our adversary, and we slide this shape over the physical representation of our circuit. And where this rectangle overlaps the gates of the circuit, we take these gates, put them in a set, and submit them to Fiesta to determine the advantage of the adversary. So we allow different shapes. This first one, for example, for lasers, this could be assumed here for electromagnetic fault injection. And here we have a practical example, so how it would look like when you visualize it on a real GDS2 file, which is a physical representation of a circuit. This here is the AES box masked with a few registers, and here we have limited our adversary to fault-only registers. And what you can see here, this, for example, would be a position where you have an overlap of the shape of the rectangle, which models the adversary with 5 registers. Okay. We did also here a few case studies, and yeah, I think you can summarize our results there that always the adversary with the largest shape was the most powerful, independent of the implementation we have tested. Yeah. Our key contributions are that we provide a scalable security assessment in the general random fault model, and we allow the automatical derivation of adversaries based on some physical properties of the circuits which should be analyzed. Currently, we lack support for detection-based circuits. However, we work on that. And to open research questions somehow are how can we derive probability distribution of fault combinations that are realistic? So how should we model our adversaries, the probabilities of our adversaries, and the major question is this model actually mirroring the reality? Or do we need some different, or do we learn, at least when we apply this model, something for the reality that helps us? Yeah, thank you for your attention.
Thank you. Any questions from the audience? Okay, maybe I can start. If we want to model different kinds of physical fault injection methods like clock, laser, or EMFI, do we need to use different models to simulate, or can it be combined into one setup?
Yeah, that's a bit the question. So I think for these local attacks, you might be able to model it with these rectangle shapes we use here. For clock and voltage glitching, to the best of my knowledge, it's more that the location where you fault depends somehow on the critical powers and the constraints of the clock. So I think you cannot model this with the same set. You need different models in theory for all different physical attack vectors, which is a bit problematic, right, from a theoretical perspective. So we might be better when we try to figure out what is the strongest adversary that supersedes all of these adversaries. However, for this, I have no better idea than simply say we target all gates, which might be too conservative in the end.
Thanks. Yeah. Someone.
Nice talk. I just was curious, like you are considering the random model, right? What if you have a biased model? How does your model adapt to a biased model?
You mean biased fault probabilities?
Yeah.
It totally works.
So
you can configure the probabilities you want to have. You can give each gate an independent probability. You can model dependent fault combinations. Yeah, you can. I think you can do everything for the faults. However, currently we support only uniformly distributed input combination, input probabilities. This is one limitation currently. Yeah, but for
it can be adapted.
Yeah, it should be easy in the end.
Thank you. Thank you.
Can we get a microphone for questions? Other one. Any other questions?
Hi. Yes, you can hear me. Very good. Thanks for a very nice talk. One question. Like in this model, the most powerful adversary is an adversary that can affect every gate with high probability. But of course, at that point, the output of your circuit is just going to be noise. This is not actually an effective attack, right?
So can you repeat the last sentence?
Like if you have an adversary that scrambles your entire circuit, your output is random, and this is not actually an effective attack. I mean, you don't recover a key. It's just you turn the circuit into noise.
Yeah. Yes, this is actually one limitation when, I mean, for verification purpose, we have here simply assumed that effective fault is everything which changes the output, right? To derive really what the adversary can learn, you need some other methods. I think there is a recent paper from a quantitative fault analysis, something like that deals with that. However, this is really, really, really expensive when you want to do this, right? When you want to compute the information you can gain from what fault. So yeah, I agree that's the problem. That's the most powerful adversary in terms of causing an effective fault, but probably not the one you want to have. So I think we shift all these models, which says just something about the if a fault is effective, shift a bit the problem or the hard theoretical fundamental work to the probabilities of how to model the adversary, and you have to know which adversary is useful in these models. So yeah, I agree with you, bit problematic.
But it's still cool. I mean, but I thought you might be able to extend it somewhat to get a probability of like a useful fault. But it's
not now.
More work.
Not now.
Future work. Thanks.
Any other questions? Okay. If not, let's thank the speaker again. Thank you. Can we keep it for the next? Or do we have? Just collect it after the session. Yeah. So the next presentation is on fault attacks and ECC signature verification. It's presented by Kevin. Once the slides are up. Thank you.
All right, thank you for the introduction. Yeah, I think the title is pretty self-explanatory, so I first start off with a bit of a motivation. Normally, when we are looking at fault attacks on signature schemes, we are looking at the signing side, just because there's a secret involved. When we are looking at the verification, there's not really any secret that we can recover. There's only public parameters involved. So the question might be, is there even an interesting use case for an attacker to attack the verification side of some signature scheme? And one such example would be a secure bootloader. There we have on the one side something that the user supplies, which is a firmware together with a signature that corresponds to it. And on the other side, we've got some stuff that's present on the system, like the hard-coded public key and the elliptic curve parameters. And based on these inputs, the bootloader will then make the decision to either boot that firmware image, the signature is valid, or just perform a reset or some other appropriate measure. Now, from the eyes of an attacker, we will then have a malicious firmware that they want to boot. And of course, they can't really have a working signature because we assume that the crypto that is present in this bootloader is somewhat secure. So they will also supply some forged signature, which will of course get rejected. So in addition to that, they will also have to introduce some fault at some point. They can either do that in the bootloader directly in the implementation of it, or something which also is possible is that they attack the input parameters such as the public key or the curve parameters with some kind of fault. This latter example is what we're going to look at first now. Here an attacker will target the public key point or the generator point of the curve. You can see on the top right here we have a curve equation for a curve in short Weierstrass form, which is basically what we're going to look at now, signature schemes that work on curves in this form. You can see that we have these two parameters here, A and B on this curve, that basically define how it looks like. And we use these parameters then in the group law that defines how the addition works on that group. And you might notice that in this group law, we don't actually use that parameter B, but only A. And this has an interesting effect, meaning that if we provide some faulted point that is not on the intended curve, this operation will not really break, but it will just be performed as it were on the intended curve. For that, well, the parameter B is not explicitly used and is thus derived from the points kind of in this calculation. And yeah, if we supply some faulted point, it will just work as expected, basically. This by itself is nothing new. This has already been used quite some time ago to attack the signature generation of elliptic curve signature schemes. So my goal was to look into if this is something we can exploit on the verification side as well. Before we do that, let's first talk about what we get from ending up on some other curve if we apply such a fault. For that, we're going to assume now that the attacker is able to flip one or multiple bits in either the public key or the generator point of a curve. And here on the right side, again, you have some example on a curve on a really small prime field. And we have a corresponding generator point with the x coordinate 14. And now we assume that the attacker flips a single bit inside this point to change the x coordinate from 14 to 12. And this will then cause the faulted point to end up on another curve. E prime is what it's called here. And this will have another parameter b change from 14 to 64. And now what we're looking at is how easily we can solve the ECDLP, which is basically what gives the security to these signature schemes. And we can generally solve it with the Polykelman algorithm in square root of p. And p is the biggest prime factor of the order of the group that is generated by the point that we're looking at. And we can see in our small example here, for the original point g, we've got an order of 101, which is already prime, so that just stays as it is for the complexity. And as for our faulted point g prime, we only have an order of 24, and the complexity gets even much more reduced since we can factorize that. So we have a total complexity of square root of 3, so we can much more efficiently solve the ECDLP for that faulted point. Now, the next question we might ask ourselves is how likely is it to find an exploitable fault? Our assumption here in this experiment that we performed was, we performed this experiment with this orange line that's going right along the dotted blue line. And what this orange line is some experiments were performed where we just generated random curves and looked at the order of these curves and then factorized them to find the smoothness. And we can see that this smoothness of these random curves closely aligns with the Dickman function, which is a function that can be used to estimate the probability of some random number in a given range being n smooth. Now, since we don't only have one fault that we can consider quite a lot of faults if we target an elliptic curve point. If we just want to look at every possible single bit flip in an elliptic curve point on a 256-bit curve, we basically have 512 candidates that we can check. And if we then look at all these candidates and calculate the smoothness of their orders, we will see that we can be almost certain that we will be able to find at least one fault where the generated curve order will be 2 to the power of 65. This is what this point here indicates. And 2 to the power of 65, or the square root of that, is something that we can kind of easily compute. So ECDLP will be pretty easily solvable there. Now, what does this actually get us if we try to attack a signature scheme? The signature scheme we are looking at now is called ECG-DSA. This is a variation, a small one, of the ECDSA algorithm, which is a bit more common. And there's a small difference here that enables an attack. I will talk about the difference in a second. But let's first look at this algorithm now. So this is the verification function for ECG-DSA. For our attack, we assume, again with this secure bootloader example in mind, that the attacker provides the signature pair, the values R and S, together with a message. And then we assume that the attacker has already introduced some fault into the public key point P, and we call that point then P prime. And we assume that we can easily solve the ECDLP for that point. Now the first step for the attacker would be to just choose some arbitrary value for the signature value R. In this case, I just chose 1 to make it a bit simpler, this equation here. So this is basically the same equation as above, just with R set to 1. We can see that almost everything here is already fixed. This point is already clear what it is. That this left-hand side of the equation is constant. And now we only have this point x left that we need to find. Usually this is not a problem, but we know that this point x is derived from p prime, and p prime is not on the same curve as g since it has been faulted. So we are dealing with an addition between points that are not on the same curve anymore. So we have to find a solution for that. Turns out that is possible. We can quickly calculate that. I'm not going to go too deep into the details here. But once we have found this point x, we can just solve the ECDLP on that now, and this gives us the remaining signature value s, and correspondingly our forged signature. We also did this attack for ECS DSA, which is a Schnorr signature that's based on a group of elliptic curve points. And if we are going to talk about countermeasures, that's pretty straightforward. We can just use a complete group law instead that incorporates all of the curve parameters and doesn't implicitly assume them. This is something that's basically the standard for the signature generation part, but on the verification side, it's not something that's commonly used. And yeah, another countermeasure would also be just to add a non-curve test in the end. So after calculating our witness point here, we could just check if this point that we calculated is still on the curve that we expect it to be, and if not, we could just abort verification procedure. Yeah, so we looked at ECGDSA, so why haven't we looked at ECDSA? We have in fact looked at ECDSA and found that it's not that easy to perform this attack here. Algorithms differ just slightly. We can see on the right-hand side of the equation here for the verification, the role of R and S is kind of flipped. This makes the attack way more difficult or possible. And the way we approached these previous attacks was that we tried to somehow reduce this problem that we've got here on the right-hand side to a single ECDLP over a recurve. Now, if you try to do the same for ECDSA, we will see that, for example, fix the variable R to 1. We are left with this right here, where we have these 2 points, and one of them has to be faulted, so they won't be on the same curve anymore. And for the Poly-Kalman algorithm, or if we want to come up with some variation for it to solve this problem somehow, we always work on subgroups of these curve points. And now that we've got these 2 different points, G and P, that are not on the same curve anymore, we don't really have any common subgroups that we could solve this problem for. And this is why we believe that it's not really possible to perform such an attack on ECDSA. So that was the first part. In the second part, we are going to talk about some attacks that are more on an algorithmic level and target towards specific implementations. A bit of a motivation again here, why are we looking at that? You can see here on the right is a code snippet from a secure bootloader. And we can see that they already implement some hardenings here. And this is these highlighted macros. We call the ECDSI verify function, then this result is encoded somehow. We've got this FIH not equal macro, and this macro basically performs this operation redundantly so that a single instruction skip can't really do any harm here. And you might already guess what the problem with this is here, that this ECDSA verify function is of course not implemented in the bootloader, but in some cryptographic library. And if we take a look into that, we can see that at the end of this verification function, we just have this comparison here of the witness point R. We check if the x coordinate is equal to our signature value R. And if it's not the case, we just return that the signature is invalid. But of course, as an attacker, we can simply target this right here to return that the signature is valid when it is in fact not. And the hardenings here in this part don't really mean anything if we can just attack the verify function in the library itself. So this is already an example of an attack that we could perform. The question now was, can we find any more faults that are a bit more sophisticated? It might not be that apparent. So what we did was we first defined a fault model that we could just work a list of possible faults that the attacker might introduce and check what this would maybe get them in an attack. For this, we assumed that they can skip one or multiple consecutive instructions, or flip bits in persistent memory or RAM or registers. And since we wanted to look at this on an algorithmic level and didn't really want to perform a comprehensive pen test on all of the possible crypto libraries, we went to the algorithmic level and had to abstract the fault model a bit more for that, which means in our more abstract fault model we assume that the attacker will be able to skip functions, algebraic operations, tamper with comparisons. Something we also noticed is that these implementations often implement some kind of short-circuiting behavior. Example on this is, for this is on the right here again. We've got our scalar multiplication m times p, and then we can see that this function starts off by checking if m is some trivial value like 0, 1, and if that's the case, we just immediately return some constant value and skip that computation part. And this is also something an attacker could target to just skip this multiplication and perform and return like the neutral element of the curve or one of the input points. Since we are mostly looking at software implementations for general purpose microcontrollers here, these implementations also have to somehow store these values that they are calculating with, and for that they use some kind of big-end structure usually, which looks like this here on the right. Again, we've got some pointer that points to the actual data, and then we've got also a limb counter which just specifies the size of this big-end structure. And we can again target that by just modifying the pointer in some way to make it point to some Ransing constant that the attacker may or may not know, or to make it point to 0, or we could also significantly decrease the size of this value by decreasing the limb count. This led to 10 attacks that we discovered for ECDSA and EDDSA. I'm not going to show all of them here, that would be a bit out of scope. Just going to give you one example of these attacks on EDDSA. So basically the idea is, again, we've got these attacker-controlled inputs. As with the secure bootloader example, the attacker can control the signature pair and the message. And then we target this h times p multiplication, so the multiplication of this hash value here, public key point. And the fault is basically going to be that this multiplication doesn't really happen at all, and that just this point p is returned. And to now forge our signature in that scenario where we've introduced that fault, we basically just choose some arbitrary value for s, and then we can already see that there's not much left here. We need to find the value r, and since this witness point q here doesn't really depend on the hash anymore, since we faulted that, it also doesn't depend on r anymore, so we can just calculate this missing value by calculating s times g minus p. And this gives us our forged signature that will then be accepted if we manage to get this fault into somehow. Now this was all a bit theoretical. We, as I said, analyzed this on an algorithmic level. Now the question is, does this actually apply to some implementations, or doesn't it really hold in practice? So in the next step, we then checked for all of these attacks, can we somehow find a fault in some implementation that mimics this behavior that we want? And for this attack I just showed you, I've got this example here in wolfSSL, where we basically have these function calls here that perform these steps in the verification routine. And this function call right here actually it does exactly what I just showed, this h times p calculation, and it also stores the value in one of the input parameters. So this is the target, this is the source value. So if we just skip that function call altogether, we will just end up with the original public key point p ending up in this variable p without being multiplied by h. And this is exactly what you need to achieve this fault from the previous slide. We did this for all of the attacks. For 70% of them, we were able to discover some place in the implementations that we looked at where we can actually introduce such a fault. For the remaining attacks, this was not possible, but this is not really something that we are sad about. The main idea behind this was to somehow provide a guideline to the developers on how to securely implement these signature schemes if they want to defend themselves against certain types of faults. And for that, we don't need to find a possible attack in every implementation that we look at. So in this last step, we then asked ourselves, how can we defend against these attacks? We just introduced some very basic checks. This is really not complicated. We looked at all of the attacks that we found. This is now an example for EDDSA again. And just for every attack, we introduced some check that verifies that this fault didn't happen. And these are all basic mem compares, so they don't really contribute to the runtime at all. It's really a negligible overhead, and they can already defend against the low-hanging fruits. Of course, if we extend the fault model further, other attacks might be possible, but at least this gives some basic level of security, which is not really there at the moment because the implementations that we checked don't really implement any countermeasures at this point. So to summarize all of this quickly, we proved that recurve attacks are in fact possible for EC GDSA and ECS DSA for the verification side, and not only for the signing side. We also estimate the likelihood of finding some exploitable points through a fault. Then we continued to look at EDDSA and ECDSA and found 10 more attacks that are a bit more on a algorithmic level and targeted towards how these signature schemes are usually implemented, and also proposed some lightweight hardenings against them. That's basically everything I've got. Thank you for your attention.
Thank you. Any questions?
Okay, thank you for your presentation. My question is, do you do actual attack in the real MCU box? And if we do the actual attacks, how can we generate the trigger, and how can we find a precise time to inject a force?
Yeah. So we didn't really perform this on actual hardware. We only simulated it. So we basically attached the debugger and performed an instruction skip where we needed it to be. If you want to do this in hardware, you would, of course, need to somehow find a way to implement that, but it's not really something that was part of our research here. We are working on showing some of these attacks on actual hardware to also show that they are actually possible and not just in theory. But as far as this work goes, we only really simulated them.
There's a question in the back.
Hi. So you showed modifying a point and then figuring out what the signature should be. Mm-hmm. But while injecting the fault, you need to compute the signature beforehand, right? So how big is the space? How likely is it that you're going to generate the signature that you're going to be able to then fault and get successfully? Because you can have a successful fault, but just happen to use the wrong signature, right? Which would have worked for another fault.
Yeah, that's the difficult part here about this first attack where we attacked the public key point. Of course, you have to know what this fault is that you injected, and you have to kind of be able to reproduce it with a good probability. What you would do is to, as you said, calculate the signature beforehand. You try to guess, or maybe you actually know what the fault will look like if you inject it. This, of course, depends on what means you have to inject this fault and if this is actually reproducible. But yeah, this is going to be difficult if you're doing this in practice. It's out of question, yeah.
There's a question in the front.
So thanks for the talk. You showed that for the ECDSA it did not work, right?
Yep.
Would it be, maybe if any thoughts on that, if you were to inject two faults, such as both curves are faulted, would it then work again, or is this still tricky?
That's still tricky. I might, what we can do is, instead of faulting the curve points, we could also put a fault into the curve parameter A, which would then in turn pact both the generator point and public key point without actually touching the points themselves. So they would both, or might end up on weak curves. But this is also nothing that we can really use. The idea behind these attacks was, as I explained, to use the Poly-Kalman algorithm at some point, or at least the idea behind it, where we try to work on subgroups of the faulted points. And if we have two different points that are on different curves, they will generate different groups that also have different subgroups. And if we don't have these shared subgroups that we can work on between these 2 points, this doesn't really help us in finding a solution in some way.
Is it just the order for that need to be matching with the subgroups?
Could you elaborate on that?
Okay, I mean, you have this factorization, and then you get subgroups in the order of the factors, right?
Yeah.
Is it just that for both points, the subgroups, the subgroup size needs to match, or is there more that needs to be matching?
Well, the subgroup itself also has to match. It's not just the order. So we need to have the same elements in these subgroups.
Okay, because then I would have said, okay, you try, and then you get some, you need 2 things matching. If it was just the order, and then you need to inject more faults, try more, and then match stuff, such that you have the highest in both the same, but then it's not working, obviously.
Yeah,
okay.
Yeah. So I don't have a formal proof on that this doesn't work for ECDSA, so if you have some ideas, feel free to discuss them with me. I've checked some approaches, and none of them really worked. They're all documented in the paper, but yeah.
Yeah, thanks a lot.
Welcome.
Okay, let's thank the speaker again. So we have the last talk for the session. It's titled TOFA, Towards Fault Analysis of Gift and Gift-like Ciphers, Leveraging Truncated Impossible Differentials. The talk will be presented by Anup Kumar.
So thank you. Hello everyone, I am Anup Kumar Kundu. I am from Indian Statistical Institute, Kolkata. So this is our work, TOFA towards fault analysis of gift and gift-like ciphers, leveraging truncated impossible differentials. So this is a joint work with Shivam Ghosh, Ekta, and Dhiman Shah. Shivam Ghosh is from India, Paris. Ekta is from Teugras, and Dhiman Shah is from IIT Village. So our motivation. So here we basically see that classical cryptanalysis strategies adopt physical attack techniques. So here in our work, we have taken truncated impossible differentials, TOFA, and we have applied it in differential fault attacks. So all the previous attacks basically relies on the onion peeling strategy. So they require faults to be injected in some multiple number of rounds. And they basically limit on a random bit or nibble fault models. So here in our attack, we have used random byte fault model. For this, we just require to inject the fault in just one round. And this is because of this, or like using our attack, we have got the better fault penetration. So this is the ability to inject the fault in some earlier number of rounds. And we have used less number of faults than the already reported works in this area. So background. So GIFT is a SPN-based structure, substitution permutation network based. So it has two versions, GIFT 64 and GIFT 128. So GIFT 64 has 28 number of rounds and GIFT 128 has 14 number of rounds. Both of them are basically has S-box, permutation layer, and add round key in the round function. So GIFT has differential branch number 2, the S-box of GIFT, and it has bogey permutation, which is basically bad output goes to good input. So it's a 16-bit to 16-bit permutation. So you can see all the okay. So you can see here the four quotient, these are called quotient groups. So it's a property of two consecutive rounds. So you can see the quotient groups S boxes are permuted to the remainder group S boxes only. So for GIFT 64, this property can be seen for 4 QR groups. So basically there are 4 QR groups in GIFT 64. So 4 into 16 basically 64, and GIFT 128, it has 8 QR groups. So Bakshish has also similar structure like GIFT. It has both state size and key size 128 bits. It has 35 number of rounds. Each round has S-box permutation and add round key. Along with this, Bakshish has also a very unique property, which is the round keys in the round key generation process. The next round key is generated by the just right circular shift by 1 bit of the previous round key. So here we will see the truncated differentials. So in differential characteristic, we predict the intermediate differences after each round. So the differential is actually collection of the characteristics. In truncated characteristic, it predicts only the part of intermediate differences after each round. So in the truncated differential, it's the collection of the truncated characteristics. So the idea of truncation refers to the relaxation of the specification for a differential. So if we take just a particular example, in the classical differential, we can see that this 0020, it goes to specific 0020 only after some 4 number of rounds. So for truncated, it can be like, this can be any nibble value. So these are all nibbles. So 4 nibbles means total 16 bits. So it can take any nibble value. So from any nibble value, it can go to any nibble value in these 2 positions only. So the remaining 2 positions are only constant. So this is the main motivation, or this is the main idea of using truncated differential, that you can give any value, it can take any value in this particular position, and it will spread to any values in these 2 positions, so the remaining 2 positions will be constant. So this is the main motivation of truncated differential. So we have used that in our attack. So in our attack for fault analysis, so here first Z round is the 0 difference. So we basically give the same message only, and after some number of round, here we are injecting some particular difference, random byte difference actually, and the difference will propagate for f number of rounds, and it will generate some pattern in the intermediate rounds, and we will use these patterns to recover the keys for the last 2 rounds. So basically last B rounds. So here we will see that we will guess the last 2 round keys, and we will use the distinguisher here and recover the key space from, or reduce the key space from here. So for that, we introduced a admissible input difference, AID. So an AID, we have said that an AID is an admissible input difference which has the Hamming weight maximum 8, and it's a non-zero obviously. And we use the random byte fault for this case, and we have checked the propagation. So propagations means we are checking how it's spreading throughout this number of rounds. So here we, for the key recovery purpose, we use the quotient remainder group structure to reduce the key space. So for truncated cluster, we see that suppose we are giving the random byte fault in this 8 bits particular. So 8 bits means we are taking the 8 bits can be injected in 2 nibbles also, or it can be injected in 3 nibbles also. So in 3 nibbles, suppose the consecutive bit, like the random fault is spreading in this bits. So after one round, after one S box, all the bits can have some difference, some active pattern. So it will spread to this 4 nibbles from the QR group property. So in type 1, the input difference or injected fault is giving to, is like we are assuming the injected fault is spreading, or first we are injecting the fault in one QR group only. So this is type 1, and this total after one round, this total state can be represented by this. So here we can see this is 000B, which is written there. So this representation can be after one round. So this is the representation of after one round. So in type 2, we can see that, So in type 2, we can see the total 8 bits can be spread to 2 QR groups. And because of that, here total 8 number of S boxes are active. In the previous type, there is only 4 S boxes that are activated. So this is, if we just map all the clusters, and then we can see that, and these are the all possible type 1 clusters, and these are all possible type 2 clusters after one round. So after 2 rounds, this is the all possible type 2 clusters after 2 rounds, and this is all possible type 2 and type 1 clusters. So these are the possible clusters for gift 64 only. Now, if we look into gift 128 or Bakshish, so after 3 rounds also we can get some clusters or some pattern. So this set is represented by that. And we will use these 3-round clusters to get an impossible differential, and we will use that to recover the key space. So in our key recovery attack, suppose the gift 128, here it is the representation of 5-round gift 128, and here we are giving the fault in the, like suppose the fault is injected in this specific byte, consecutive 8 bits, and after that, after 3rd round, the differences are spreading in this possible bits only. So here we will guess one QR group. So one QR group has basically total 8 number of key bits, because one nibble has 2 bits for gift 64 as well as 128. So we will guess one possible key space of one QR group, and we will check whether the condition after 3 rounds happens or not. If it satisfies the condition, then we'll take that key as a possible key. We will use this for all number of QR groups, and we will reduce the key space. But here we have used a we have used a combination technique of QR groups, which I will say in the following. So after that, after the all QR groups are recovered, we have checked the condition in intermediate rounds also, and checked which are the possible keys which basically satisfies all the condition in the intermediate round. So there are total 8 number of QR groups. So at checkpoint 1, we have guessed all the possible QR groups, and we have reduced the key space. Okay, so that should be 2 to the power 8 actually. Here it's a mistake. So 2 to the power 8 to 2 to the power 5. That is the total possible key space after one round. So if we check the checkpoint 2, which is the, if we here we have combined two possible QR groups. So two possible QR groups means the total number of key space is 2 to the power 10. So 2 to the power 5 plus 2 to the power 5. And after checking the intermediate third round difference, the total key space reduces to 2 to the power 8 only. So we got the key space of two combination of QR groups, and after that we will combine 4 QR groups. 4 QR groups means two combination QR groups. And this has total key space 2 to the power 16. After checking the condition, it will reduce to 2 to the power 11. And if we check the other condition, like here now we will take the all possible QR groups, and this has 2 to the power 22 total key space size. And after checking all the conditions, this will reduce to 2 to the power 0, that is unique. So this is the key recovery attack for gift64. So as I have said that for gift64, you can see there are two possible intermediate conditions only which we can check. And here also we have taken the help of quotient remainder group structure, and we have reduced the key space. So for for Bakshish, we can use another condition also. So after applying the previous procedure, so after reducing the each QR group, for Bakshish we will use the key relation, which is from the previous round key we can determine the next round key by just circular shifting one bit. So here we have seen that if we use the round keys for QR groups, then for a single QR group, 3 bit can be equated. So we can take that 3 bits as a condition also. And if we combine 2 QR groups, then 8 bits can be checked. For 4 groups, 32, and for total 128, obviously 128 bits will be can be checked to reduce the key space further. So we have taken the combinations and we have checked the pattern and key relations after 2 rounds. So this is the table for gift 128 and Bakshish, and this is G means the total number of combinations which the total number of reduced key space after taking that many combinations, like G many combinations. So in the first column, this is the first QR group. This is the combination of 2, combination of 4, and combination of 8. And this is the time complexity of the attack. So now I will discuss the practical implementation on Chief Whisperer. So here in the practical implementation, we have induced the fault in the, for gift 120, we have checked that we have induced the fault before 35th round, before the S box of the 35th round. So we have checked suppose this is the triggering point. Triggering point means here between this and this, the fault is injected. So in the voltage consumption, we can check that without clock glitch. Suppose this is the total, this is the graph. And if when we do clock glitch, then this is the graph that we get basically. So here we can check that there might be some operation which is basically violated or due to fault, and because of that we see the graph is basically a little bit low than the previous one. So this is with clock glitch, the graph, the voltage consumption. So here we have used the ATX Mega, this microcontroller, and we have used our attack is faults can be anywhere at max 3 consecutive nibbles. So we have checked that the only 38% of faults are injected, and that leads to faulty results. And approximately 80% of the injected faults can affect at max 3 nibbles, and that is the requirement of our key recovery attack. So this is the implementation results. Here, after giving the faults, this is the number of times, and this is the reduced key space that we are getting from the simulation. So here, obviously the ciphertext and all, and those are those are taken after doing the fault only. So this is the summary of our key recovery attack from the previous. So conclusion is, here we have introduced TOFA, the first fault attack on gift and Bakshish using truncated impossible differentials. So we have achieved the practical key recovery on Bakshish, on gift without fault peeling, without onion peeling of the cipher. and it requires a fixed number of faults. So for gift 128, it requires 3 faults. For gift 64, it requires 22, and Bakshish, it requires only 4 faults. So overall, TOFA is the best fault attack on this on these ciphers, offering a new insight on the fault attack vulnerability of bit-oriented SPN-based block ciphers. So thank you. And this is our artifact link. So you can check all the implementation codes, and the simulation codes also are given to there in the GitHub repo. So thank you.
Thank you. Any questions? Okay, maybe I can start. So you run the attack on software implementation, and you used instruction skipping fault model mostly. Considering the ciphers that you're attacking are more suited for hardware implementations, how do you think the attack would work on hardware implementations with different fault models? Typically, instruction skip is not the ideal model for that, right?
Okay, but as long as we can see some truncated patterns within that cipher, like within the propagation of the cipher, obviously, like I believe we can check that pattern, and we can use that, we can use our model in that cipher also. If we get the pattern, suppose after inducing the fault, we are getting some pattern after some number of rounds. So from that intermediate patterns, or like from the last pattern also, we can reduce the key space of the cipher, and we can do our attack from there. So as long as we can get the truncated pattern, we can do that. And that can be used via other fault attack, like other hardware, other methods also in the implementation, practical.
Okay, thank you. Questions? There's a question there.
Thank you for your presentation. So my question is, do you think that your work opens an avenue for like future potential fault attacks based on this impossible differential concept on other symmetric ciphers, perhaps non-bit oriented?
Okay. So you are saying if whether bit-oriented ciphers, without bit-oriented ciphers, other ciphers can be
like more used symmetric ciphers, like, I don't know, yeah. AES, presence, yeah. And so on and so on.
So, so your question is whether that can, like our attack can be applicable on that also. Is this your question? Okay. Yeah, so that can be done, but the problem is here for this bit-oriented ciphers, we can get the pattern after more number of rounds. So because of that, we can penetrate more number of rounds, as we can see here. So but for AES or other ciphers, as there is mixed column layer in between, so it spreads more early. So obviously we can use the truncated patterns in the intermediate rounds, but you cannot get that many round fault penetration depending upon our attack. But it can be applicable, obviously.
Okay, so it's about computational power.
Yeah.
For like this more, let's say, complex symmetric ciphers.
Yeah, computational power as well as, yeah, you can say. And I'm saying that the number of rounds cannot be bigger. Like the fault penetration, you can't give within, like, you can't get the fault penetration for more number of rounds. It will be less than bit-oriented ones.
Okay. Thank you.
Yeah, thank you.
Any other questions? Okay, then thank you, and also thank you to all the speakers in the session.